Okay, so let's just start the second talk of today, the second and last. Just for the sake of people in the future who doesn't know me, my name is Daniel. I attended to the first bootcamp. I recently teach in the bootcamp in North Carolina, and I'm here now to talk about library structure 5. And at this point, I still don't learn these things pretty well, so please don't judge me too hard. And let's try to figure this thing together. So I think we are very, very lucky to have people like Andrea and like Rocco and Bikram who have like deep understanding of Rosetta. As deep as possible. Because Rosetta is so big that sometimes it's really difficult to figure out how to write things on it. So it's great to have this opportunity to give a fast-forward introduction to Rosetta to people. And hopefully many of you are going to become at least active developers for your own projects and not just users of Rosetta, right? So I think that's the target of this thing, being able to create new tools, new recipes for Rosetta, but not at the level of Rosetta scripts, right? So that's for people who only can write XMLs. But now probably you will have the power of write your own cooking recipes here at more advanced levels. So the thing that I'm talking today is this thing that we call Libraries 5, and essentially what I'm going to talk is about some things that are inside of Protocols 3 and Protocols 4. And here's where the thing starts to get weird, right? Because probably, or hopefully somebody explained to you that due to design, due to the way Rosetta was designed, things can compile in layers, and things that are up in the layer can call things that are down the road, but they cannot call them things that are in the same layer. So they made this design decision because it prevents to have circular dependencies, right? So this allows, in principle, for faster compiling times and to avoid to do like weird things like, libraries that call libraries that at the end call itself and then cannot be compiled, right? So, but due to this, the problem is like, no, let's say that you want to write a protocol that uses all the other protocols that exist in Rosetta, right? So that means that you will need to create a new layer of protocols that is able to call all the things that are before it, right? So now we are going to be in protocol trees where things start to get interesting because it can call other protocols, it can call everything that is in core basic numeric utility, right? And now it gives us the power to start cooking with Rosetta, not to simply apply independent movements to macromolecules, right? And so if we look into Protocols 3, to do this, you essentially the only thing that need to do is to go to source and take a look to Protocols 3 source settings, which is the file that says which things are going to be compiled. And over there, you're going to find things that are called simple moves, simple filters, toolbox, analysis, constraints, loops, kinematic closure, normal mode, etc., right? And if you think a little bit about this, you can understand how these protocols things happen, right? So people came and start cooking with Rosetta, putting things together, and eventually they figure out that they want to do more complex things that actually use things that are in Protocols 3, so they come and put Protocols 4, right? And like that, it starts complicating things more. So now, if you're going to design a protocol, probably you should try to figure out where it should be, right? Because sometimes people come and the easiest thing to do will be to put things in Protocol 6, right? Or Protocol 7, because that seems to have everything down the road accessible to it. But that doesn't actually mean that you need everything, right? And if you do that, well, you're overcomplicating your protocol. So you will like to be, I will say that when you create something, you probably want to be as lower in the hierarchy as possible, right? So that you decrease the flexibility of your protocol, but you also decrease the complexity of it, right? Because you are calling less other things, which are already pretty complex.
On that point, the lower down you put it, the more possibility there is of someone else calling your protocol. If you put everything in Protocol 7, then nothing else can call your protocol.
Yeah, that's a very good point. I'm going to show you an example of this by the end of this talk. So So the thing I'm going to do here is like Andrew created these slides, and he kind of tried to highlight some of the protocols that are under protocol tree. This is not all the protocols that are in protocol tree that are useful, but I mean these are the ones that you should be aware if you are going to do like things with Rosetta, right? So one of them is like the back rotamer mover, right? So this is essentially the main mover of Rosetta, right? So this is the one that takes the rotamers and changes them, right? Well, this is essentially the most, probably the most useful thing that Rosetta can do, because it allows you to determine which one is the best sequence that you put into a given fault, right? And essentially, this invokes back rotamers, right? And maybe many of you have used this before using Rosetta XML. Now, because of the powers that you're acquiring, because when I say this, you can go and use directly this function now. And well, as important as this one is the min mover, right, which will allow you to take a pose and minimize it in different ways, right? It can essentially take a move map that says which parts are allowed to move, and it takes minimizer options, which allows you to take different ways of minimizing the protein. And it allows you to put a specific score function, which will change the way in which the molecule minimizes, right? Essentially, these two operations should be enough to build almost essentially any protocol, right? But we are lucky that people have been working with these things before, and they have figured out another combinations of things that will allow you to make more complex operations with proteins.
Sorry, one little point. The pack rotamers mover is calling the packer, which lives in the core. The min mover is calling the minimizer, which lives in the core. So there's still a more fundamental algorithm than both are calling.
So that's a difference, right? So you can always, well, this is what happens when you're building something like Rosetta, right? So somebody else has figured out how to put the components together, such as you call a function, right? That makes the packing, minimization, and everything all together, returns to you an answer, right? But if you really want it, you could go, in principle, you could take just things that are, you could take out all the protocols and just build anything just from whatever is before, right? Just from core, essentially. It will take some time, probably, right? But in principle, the fundament of Rosetta will be just everything below core, right? So from core to the objects, it will be what builds Rosetta. You could take that and build anything in protocols if you have enough time, right? And a skill. But the idea of protocols is to help people to build more complex things and to build over Rosetta. So now, here probably it's important to say this. Now we have PyRosetta, right? And PyRosetta can also access all the functions in core. It can also access all the protocols. The only disadvantage probably of programming with PyRosetta, though it seems easier, right, is that it's very difficult to build on top of it, right? So I'm a person who likes to prototype in Python because it's very easy for me to do it. It's very fast. You can do it in real time. You don't need to compile, right? But the disadvantage is that if you don't move that code to C++, then essentially you don't allow other people to use the algorithms that you generate, right? So that's why it will be important to eventually move your code into C++ or directly make your code in C++ and have it well documented, put well commented functions and everything so people can come, right, and use it. And if you put it in protocol 3, probably a lot of people is going to use it, as Vikram says. If you put it in protocol 7, probably nobody is going to use it because it's too high in the hierarchy and it's very difficult to build with it, right? So, okay, let's continue. You also have here movers that allow you to move the backbone by perturbating the phi and psi angles, right? There is a very special move that is called the share mover that allows random perturbations of the backbone. And this is actually very important for ab initio folding of proteins. So you can go to the article and take a look why they decided to build this thing. But again, you see this thing just like modifies phi and psi angles, right? So you can, in principle, just do pose set phi, pose, right? Psi, set psi, and that's it, right? Then there is the fragment mover, which is fundamental for the way in which Rosetta makes ab initio folding, right? So we are going to discuss this a little bit later. You have the torsion degrees of freedom It allows you to perturb the torsions of a pose and do repetitions of the perturbation and use a complex Monte Carlo to decide if you accept or reject the changes that you're doing in the pose. You have a ramping mover, which is crucial to move into a Monte Carlo style minimization, in which you can ramp, right, the values of essentially the weights of the scoring function in order to minimize or to perturbate minimums of the energy and escape and be able to jump into another minimum of energy. You also can set constraints to your protein, right? Or to your molecule. It doesn't need to be a protein in Rosetta. So you can set constraints that allow to modify, allow you to constrain the protein to a specific conformation and then to bias the energy if you move from this specific conformation. You have a mover to superimpose, which is essentially like what you will do with an RMSD rotation. It's a very simple mover that only allows you to superimpose molecules if they have the same number of atoms, right? And on top of all this, you also have the symmetry movers, right? Which is a special class in which you can make all the things that we just talked about, put in symmetric molecules. And that's a design thing that Rosetta has. In principle, symmetry should be an intrinsic operation in molecules, but the way in which it was designed in Rosetta, we don't have real symmetry. Essentially, what we have in Rosetta is like you have a pose, and when you apply symmetry, it actually makes copies of the poses inside of the memory of Rosetta. And then every time that you apply a change in a symmetric pose, what you have is a formula that tries to calculate the minimum number of interactions between the copies, right, to calculate the energy. But it's, let's say you're changing a rotamer in a symmetric pose, so you are actually changing it in the asymmetric unit and in the symmetric copies that you need to make the calculation. So this is not the only way to implement symmetry. If some of you is skilled enough, it would be great if somebody goes and implements like you know, an asymmetric unit box that has the correct geometry. Then instead of using like copies, it uses just pointers to the same objects. Let's say to the other atoms in the molecule, right? And it can actually calculate the auto-interaction of the molecule. That would be a great implementation. Molecular dynamics uses this method, but we don't have this kind of thing implemented in Rosetta, right? Okay. We also have here simple filters. So many or most of you should be familiar about the filters that we use in Rosetta XML, right? In Rosetta scripts. So filters are these things in which you have an apply method that evaluates a pose but cannot change it because the pose that you pass to a filter is a constant, right? So it evaluates a pose and it returns true, false, or a value, right? And usually you can put a cutoff in a filter, and the cutoff will be used to evaluate if the filter passes or not, right? So this is the same thing that you are calling when you are executing a filter, or many of the filters in Rosetta scripts. Not all the filters exist at this level because some of them depends on other filters, right? So they are higher in the hierarchy. But most of the most useful filters are in these simple filters. Some of them are like the score cutoff filter, right? Which will tell like if the pose has this energy, it passes. If not, it doesn't pass, right? Okay, then you have protocols toolbox, and this actually is not the complete description of what is in the toolbox. Alex put a lot of code recently, well, in the last 2 years in this toolbox, which is incredibly useful. Like things that allow you to calculate faster MSDs, things that allow you to calculate new ways to store fragments, a lot of things. So later, when you have time, go and take a look to the toolbox. Most of the things that you are thinking about coding, somebody else has already thought about introducing them. And if you think about something useful, I mean something generally useful for people, please go and put it in the toolbox. It will be really great. Let's see. Okay, so yeah, here you have tools that will allow you a little bit more complex operations, like clustering, evaluate decoys, select residues by different layers.
So my friends do by layer now lives in core.
Well, before figure out a way to move this.
But this is another thing to it about the modularity of Rosetta. If you develop a protocol and it's very, very useful, like layer design was, and part of it could be used in other things, it's good to split it up into pieces and put whatever pieces you can as low level as you can so that other things can use them. So the actual part of layer design that selects the residues by the layer, I would of course that other things can use it in the layer selector.
But that obviously requires a little bit of thinking and re-engineering of the code. And also, if you're going to do that, be very careful because, I mean, you want the code in core to be like well-written, you know, to have comments. And Andrew usually checks all the code that you put in core, and he's going to yell at you if you put something that is not useful or that is not logical. I had that problem before. So, I mean, just, yeah. Be careful. And you have, I mean, all these other things, right? Like calculate cell bridges, calculate surfaces, pack stats. We have here the creator of pack stats in the back. And well, I mean, let's try to see what we are, how this fragment insertion will be useful. So. This is probably one of the most important parts of Rosetta, or at least for me is. And so it's essentially the main protocol that we use to make ab initio folding, right? So in order to make ab initio folding, essentially what we are doing in Rosetta is that we are taking sequence, right? And then we are trying to figure out which fragments that have been previously observed in the PDB correspond to this sequence. And then we are making a list by windows. We are separating this sequence into fragments, right? And then we are calculating by windows which ones are the fragments that best fit to the sequence. And then we assemble them together. And we try to determine which assembly of different options of fragments, right, gives you the lowest energy. So let's go a little bit more in here. So the idea is that you have a database that we call the BL, right? And then from there we have residue fragments that are usually 3 and 9. That's the usual way in which we assemble fragments in Rosetta. So what we are going to do is that we are going to have some method in which we compare the sequence of the protein that we want to fold to the fragments in the database, right? And we are going to choose the best ones for each window of the protein. So if you have a protein that has a size of 9, you will choose 9 minus 3 minus 1 fragments of size 3 and 1 fragment of size 9, right? This is a hypothetical case, right? And what you will try to do after that is to assemble them, okay? The problem is how do you actually choose the fragments, and that every year you have more structures in the PDB, right? So this database changed. So back then in 2003, I think, they created one database. And this database wasn't that big, and as we usually do things, I guess it happened in the same thing in the same way at that point. They just start assembling different programs in order to get the thing done, right? And what this ended up being is a gigantic Perl script that uses many other programs in order to choose the fragments for a given sequence. So running the old fragment picker is actually really, really a pain. It's a pain. So it needs a lot of like third-party programs, and it uses that Perl script. These things are not in C++. I don't know if there is even a part there that is actually in Fortran. So it uses all kind of things. The thing with this fragment picker is that it's very fast, probably also because the database was much smaller in 2003 than what will be right now. But it's very, very fast. if TJ is around in the lab and you're really interested into the fragment picking thing, you can go and talk to him about what will be like the advantages of using the old fragment picker, or the new fragment picker. But in general, the old fragment picker is faster than the newer one. Okay. The problem is that if you go and you start your lab and you want to use the fragment picker to fold proteins, and you try to put the old one, it will take you a considerable amount of time. I mean, a really long time probably to set up it to work properly. In our lab, it works in the digs, and it works in the digs only. Okay? Some brave people decided to write this new fragment picker, which some people like and some people doesn't like, right? There is this thing which is more logical, it has a more structured way to work, it has a database scoring, it has structure to picking, collecting, and then selecting, and it only requires very few things. It requires the file sequence profile, FASTA, the BL database, right? So the BL that this new fragment picker uses is from 2008, and it contains like 9,500 proteins. The other one, I don't remember, I think it contains like 3,000 something. And okay, this is actually not important, this one, right? And essentially, this is how it works. Okay, before going there, let me tell you something about the old fragment picker and the new fragment picker. So if you're going to fold proteins, and you use the old fragment picker and new fragment picker, you will discover that they give slightly different results. So that means there are proteins that fold with the old fragment picker that do not fold with the new fragment picker. And this seems weird, right? But there are proteins that actually fold better with the new fragment picker than with the old fragment picker. This is not completely logical, because if you think the new fragment picker has more fragments than the old one, right? So now think that if the old one has less fragments, every time that you go and choose your 200 fragments for a given position, probably you get more diversity of different fragments, right? So if you go with the new fragment picker and you choose fragments for the same sequence, probably you choose more similar fragments that match to the sequence, but probably these fragments, in some cases, are not the correct fragments. And because you lost diversity, you lost the opportunity to fold the protein properly. But if you choose the correct fragment, now you have more fine difference that allow you to fold the protein correctly, right? So in one way, it allows you to fold better. In the other way, it probably is forbidden you to find the correct conformation. And this is because one of the principal things that the fragment picker uses to select the fragments is the secondary structure prediction. Yes,
sorry, this does raise a general point. If you're developing an algorithm that's intended to replace a previous algorithm, this illustrates the importance of figuring out apples-to-apples comparisons that you can come up with. This is a case where we replaced an algorithm and we replaced the database at all break zones. And we have this apples-to-orange comparison, so we have no idea which of these two algorithms is actually better. So when you're developing, think about not just unit tests and integration testing, but also ways you can benchmark whatever you develop that allow you to actually say whether it's better or worse than what came before.
That's actually a very good point. The problem with this thing about for folding proteins is like, probably the only benchmark that you have is like how many proteins it can fold, right? But it has so many variables. I mean, it's so much a cooking recipe that it's very, very difficult to actually figure out if you're doing the same thing or not than before, right? Because this is like the different score types that the fragment picker used to determine which is the best fragment, right? So there is the sequence identity, the profile score, the secondary identity, the secondary similarity, the RAM score. There is a lot of things, right? And now the different weights that you give to each one of these is going to give you a difference in the fragments that you pick. Plus, you're changing the database, right? So the fragments that you're choosing may not hold any relation to the fragments that you were choosing before, right? So, and in top of this, you will find like there are different ways to choose the fragments, right? So there is the best fragment protocol, right? So which is going to come and make a secondary structure prediction of your sequence. Then if there is a part of the sequence which is predicted with certain probability to be certain secondary structure, you're only going to choose fragments that have that secondary structure. And secondary structure prediction algorithms are actually not perfect, right? Sergey has found recently that many times the secondary cypred will predict a strand as a helix. And that completely breaks the protocol, right? Because even if it is correct, because you didn't include a single fragment that represents a beta strand, you are not going to be able to fold the protein. And it's not a problem with the Monte Carlo search. Monte Carlo, of course, is going to find the minimum if you allow enough time to walk, right? It's a problem with your fragment picking. So we have found many, many times that our inability to properly fold proteins is just because we don't choose the correct fragment for the correct chunk of sequence. Yes?
Is it going to take much more time to pick fragment, not based on secondary? I mean, why do we use the secondary structure?
No, we are still discussing that, but you need to think back to 2003 or before. Will was there probably. Or will arrive a little bit later to the lab. But you need to think that computers weren't that powerful. There was not that much memory, so they had to make a decision, right? And the decision is kind of strange. So they choose 3 and 9. So probably 3 and 7 will also work, right? Or 5 and 7. And they choose to use 200 fragments. And they made more decisions. Decisions like using only certain number of fragments at the beginning of the protocol, and then a different number of fragments by the end of the protocol to refine and kind of that. And I think that all these decisions probably were made in basis of like the computing power that they had at the time, right? But I totally believe that we could re-engineer the way in which it works to make it more efficient. Like choosing fragments from all secondary structures, kind of that, right? I mean, in principle, it will be easy, but it requires research, right? Because as Vikram says, how do you really prove that you are doing something that is better than before, right? I mean, what is your benchmark? And then how do you choose like the best parameters in order to make it like time-proof, robust in the future, right? So I think that if somebody takes this as a project and sits there with David Kim and Sergey and everybody to try to figure this out, it will be really, really useful. It's just like we don't have anybody except Sergey thinking onto this right now, I think.
This also is algorithm development in general. We should revisit the paradigms every 10 years or so because computers change. When this stuff was developed, the paradigm in computing was you've got a single core that's going to do a lot of things, and cores are getting faster.
And just to give you a quick example, right? I mean, the fast-forward folding protocol is a re-implementation of this thing for the case of de novo design, right? Because, I mean, when I saw this thing and I was thinking, like, why do people will go and try to fold proteins using the common folding protocol if you can make a much quicker test, right? Because obviously you know the structure that you're targeting, right? So you can use that to prune your fragments and figure out if with fragments that are similar to your protein you will be able to fold it. Because if you cannot do that, you cannot do the ab initio folding, for sure, right? And that's how Enrique and I created the fast-forward folding protocol, and that makes much more sense in the context of protein design, right? When you know the target. So all these things, with a little bit of thinking, is I think we have reduced so much the use of Boeing that now most of the time the queue is empty, right? When before, most of the time you couldn't run things in a week because the queue was always full, right? So, I mean, that kind of things really are really useful for us. It really makes us progress, but almost nobody's working on it. So it would be great if you can go, if you are interested to go and work in these kind of problems. And well, you have these different ways to choose the fragments, and I cannot tell you which one is the best. Usually people think the best is the one that allows them to forward fold the protein. But I mean, that doesn't necessarily is true, right? Because to forward fold your protein in the computer doesn't make it fold in the real world, right? So choosing one way or the other way, I mean, I give you the fragments that are similar to your protein and probably it will forward fold. That doesn't mean it's going to forward fold, right? So we need better ways, but this is the best we have right now, right? Okay, so the way in which this works, and I was going to take out these slides, but I leave them there so you can understand a little bit what I mean when I say cooking recipe, right? So make sense of this. The stage one is to insert large fragments into the protein, right? Make a scoring using a score function that works essentially only in centroid mode, right? And use 2,000 cycles until you change all the 5 psi angles, or until you change all 5 psi angles. So essentially, you come to your extended protein. You insert randomly, in random positions of the sequence, a fragment. You evaluate if the energy improves or not, right? And you stop either if you do 2,000 cycles or if you already change all the 5 psi angles in the protein. So this stage is known as collapse of the protein, right? It's to go from the extended chain to something collapsed. So then you go and you do fragment insertion again, just that you change the energy function, right? For one that is more expensive. Then in the stage 3, you come again and then you insert fragments again, right? But this time you make the scoring function a little bit more complex. And you can alternate between two types of scoring function, and you can alternate cycles, right? 2,000 cycles for one, 2,000 cycles for the other, right? And then
is it doing a Monte Carlo search for one and a Monte Carlo search for the other, or is it alternating a Monte Carlo loop?
Oh no, you are asking me a question that I actually cannot answer. And then you come to the stage number 4, in which you finally, let's say you folded your protein with the large fragments, and now you come with the small fragments, right? The small fragments are usually, well, it depends. No, there is no way to say that they are more diverse. They just allow you like more finer tunings, right? Because instead of changing a larger fragment, you are changing just a local fragment. This is very important because think about this. I mean, it's almost weird to make a Monte Carlo search in the fragment space, right? Because you are actually not following the direction of the descending energy. You are working in who knows which space, in the angle space by Neimers, right? So when you are making smaller changes, it's more possible that you can make a good change in the Monte Carlo space. When you're moving Neimers, you have this protein which is almost locked in the correct position, right? But you move a Neimer, and now you suddenly, because of the lever arm effect, have a protein that has a completely different conformation, because all the change propagate along the chain, right? So in the last stage, you are doing these small changes with trimmers, right? And then you are using another scoring function. And
the general convolutional algorithms, it is worth paying some attention to theoretical considerations. This Monte Carlo search does not obey one of the tenets of Monte Carlo, is that you need moves that obey detailed balance.
yeah.
But it approximates detailed balance well enough probably to be okay.
But that essentially breaks the complete idea of doing a Monte Carlo search, right? I mean, yeah, I mean, it works, but it's not thermodynamically correct.
If an algorithm works, it works, which is fine, but sometimes by considering theory, you can make it better.
And so, and then at the very, very end, it uses FastRelax in order to try to get the best of the protein, right? So I almost bet you that you can go and imagine a different way to re-implement this thing in 4 stages or in 7 stages, or probably in 3, that will also for proteins with certain probability. So it's just what Bikram said. I mean, this one is the best protocol we have now. It doesn't mean that it cannot be improved. I mean, it just needs somebody brave enough to go there and to try to make another protocol that probably is more logical. If somebody can come with a protocol that obeys detailed balance and uses fragments, oh my God, I mean, the possibilities are great, right? It's not easy to see a relation between changing fragments and thermodynamics. So there you go.
I think there are, they have the math, there was a group that figured that out, but the other thing is we've got all this other stuff that's been developed since 2003 for manipulating the vertical structure. What happens if you mix fragment insertion moves with other types of moves? We don't know, but if you start playing with protocols that use other means of manipulating the vertical structure, maybe.
Okay, well, in principle, using protocols tree, you can make all these things, right? And hopefully in the future, some people can move this to protocol ones, because I mean it's one of the main operations of Rosetta, right? And well, now we are going to talk about just briefly about loop modeling, and we're almost done. Essentially, we have 2 main algorithms, and well, yeah, I know this sounds lazy, but I'm going to allow the expert to talk about this. The
idea with CCD is It's usually fragment based. You find a fragment that approximately fits your loop geometry, and then you're basically using the minimizer to just pull that fragment into the correct geometry to fully fit. Oh, sorry. And in the interest of time, I think that's about all that really needs to be said about CCD. Because it uses the minimizer, there's some expense to every. The author of the other There's some expense to every instance in which you use it, but it is commonly used.
And this is just a cartoon movie of how CCD works, right? So essentially, you have the loop, you know the length of the sequence that you want to put there, that you want to try, right? And you have two fragments that you want to close. So you start in one of the sides, and then you perturbate the angle, the phi and psi angles, until you finally close on the other side. There is some math involved on how to make this calculation, but it's pretty simple. Then we have the one that Bikram is author of.
Well, I didn't develop the original kick, but I wrote the generalized version. The idea with kinematic closure is you've got some chain of atoms connecting two endpoints. If you have n dihedral angles in that chain, you've got n degrees of freedom if you didn't have this endpoint constraint, if you just had a floppy chain. But because you've got the endpoint constraint, you've got a rigid body transform from the start of your loop to the end. And that takes 6 degrees of freedom out of your system. So you actually have n minus 6 degrees of freedom that can be perturbed. The idea with kick is perturb all of the degrees of freedom however you want, random perturbation biased by the Ramachandran map, fragment insertion, whatever else you like, but then pick 6 of the degrees of freedom and solve for them analytically by doing linear algebra. The linear algebra is handled by libraries in core. There's something called bridge objects in core, which just does that. Bridge objects doesn't know anything about protein geometry. It just knows you've got a chain of atoms with certain bond lengths and bond angles. Because it's doing this analytically rather than by an iterative search, it's super fast. Every closure is almost instantaneous. Any attempt to close will produce anywhere from 0 to 16 solutions. The linear equation, or the equations that you have to solve can produce up to 16 solutions. So afterwards, you need some way of picking a solution from the solutions that you got, and that's usually done by energy. The classic kick operated on alpha amino acid backbones. There were hard-coded assumptions about alpha amino acid backbones. My version, the generalized kick, operates on any chain of atoms that you connect in Rosetta. So you can use it to close. You can use it to close backbones, but you can also use it to close loops that go through disulfides, as well as all sorts of non-canonical stuff.
Thank you. And well, this is just a graph that tries to show that kinematic loop closure actually works, comparing it by to the other protocols, right, and showing that it reproduces some of the crystallographic loops. But I mean, these are not the only loop modeling methods that we have. We have a joke in the lab, I think, that this is just like another loop method, right? So essentially, that means like this loop problem is one of the hardest one, and probably nobody has been actually able to solve it. Modeling loops is super hard, and almost every developer has come at some point to try to build a method to put loops in proteins, right? So there is loop hash. Alex has his own Cartesian version of loop hash, which is an improved version over or at least one that works better than the original version. I have a version also to build loops. So almost TJ has a version. Almost everybody has a version to model loops, right? So I mean, if you don't buy the loop methods that are there, why not just go and create your own method? No, that's not true. Hopefully somebody come with a good loop modeling method. The problem that we have here is like only somebody can prove that has a robust method to build loops or to predict loops. We are stuck with the current methods. that we have there, which essentially are just like either you evaluate with Rosetta, you create some loop and you evaluate it with Rosetta, or you copy something from the PDB and you evaluate if it fits your structure, and that's it. And we have also this relax protocol, right? So we have several ways of relax, and probably the most used by all you is this FastRelax protocol, which I mean, oh my God, there was an explanation here of why FastRelax works. I think the only reason because it works is like, usually when you're using kinematic minimization, you can fall in these energy minimums, which is kind of difficult to escape. But if you are near to the global minimum, right, to the crystallographic minimum, whatever, then the only thing that you need is to some perturbation, and it doesn't matter in which reaction coordinate you make it, just some perturbation that allows you to jump from this minimum into the one that scores the best. So essentially what FastRelax does is that it ramps the repulsion of the atoms, right? So people understand this as like if you were doing all the atoms in your protein smaller at the beginning, and then you were growing, inflating them until they reach the real size. That's a physical way to imagine FastRelax, right? And you go cycles of this. So essentially, you have your protein that this is the best thing that you can get with normal kinematic minimization, just rotating side chains and everything, but you are not in the perfect configuration because probably you don't even have the rotamer in your library, right? And now you go into the space in which you will allow the thing to compress the atoms, reaccommodate things, and then start inflating them, right? And finally allow everything to lock into the correct position. The thing is that FastRelax usually gives much better energies than any other relax, and the configurations that you get from it are the most similar to the crystallographic structures. So it does work. Some people think that they know why it works. I think it's just because, as usual, if you allow some perturbation in a reaction coordinate, you can escape minimums and go into other minimums. Something that is very important is that after you go to FastRelax, probably you cannot return to the kinematic space purely, because now you can imagine this as you were moving before in the space in which Rosetta likes to move, right? In this torsion space and everything. And now you apply this FastRelax protocol, right? That allows you suddenly to jump probably into another layer of, in a different conformational space, right? And this sometimes allows you to move into places in which you have very optimum energies, right? But you cannot do the reverse transition because this conformation doesn't belong to the space in which Rosetta was parameterized. So be very careful when you jump into FastRelax and you want to jump back into moving angles.
I wouldn't phrase it like that. I'd say that the energy calculations in the space accessible to FastRelax is as valid as anything else in Rosetta. But if you're doing Monte Carlo searches, you need to do apples to apples comparisons. So if I have an Monte Carlo move that moves me from FastRelax minimum to
Or Rosetta minimum.
yeah, or just a place that results from a fragment insertion move or something like that, then I'm doing an apples to orange comparison. If my move is instead do a fragment insertion move and then do a FastRelax, then it might be more of an apples to apples.
No, I completely agree.
Yeah.
And
One thing about why FastRelax works, proteins have an overall funnel-like folding energy landscape, but it's very rugged, which is why we can't just roll downhill at that global minimum. A lot of the ruggedness comes from the FA rapid term. So if we ramp down the FA rapid term, we're effectively smoothing the landscape and making it more possible to roll towards the global minimum. And then if we ramp it back up again, we can find the precise slope that we just roll through.
Yeah. I don't know if that's actually true, but yeah. There you go. You have FastRelax, and you have these things in protocol. You have also in protocol street. You have also these things for analysis. So I mean, just you have also the normal mode relax mover, which Hambom implemented recently, which has been very, very useful to refine the structures of proteins, right? And then on top of this, I also have to talk about protocols for it, but if it took me like an hour to talk about protocol street, you can figure out that I cannot spend this next 7 hours talking about protocols for. So instead of doing that, I just decided to tell to you that, I mean, there are very interesting things here. So there is docking, ligand docking, motifs, grafting, domain assembly, membrane, pulpy tail, etc. And now here the thing that Bikram was saying before, you can see that there is a grafting here this is not the grafting that we use in the Baker lab. This is another grafting that is there. I know I wrote with Alex the epigraph that essentially everybody uses. Now the thing is like, for some reason when people talk about grafting, they talk about this one and not the other one. And well, quite probably because this is in protocols 3, well, protocols 4, right? And mine is in protocol 6. And I don't think that anybody is going to build on top of that one, right? So I may have made a wiser decision if I put it in protocols 3 or protocols 2. But I mean, I decided to put it in protocol 6 because it seemed easier. But it actually doesn't use almost anything inside of Rosetta, I mean, except core. So probably it can go even to protocols 1. So, bad design decision. I'm not going to move it. And yeah, and then, well, there you go. So if you want to do docking, you can go and use this protocols docking and try to use a docking. But my recommendation is please don't use it. Better use Will's docking, which is much better, but probably is not in any protocols, right?
This is a problem in Rosetta. Typically, the first protocol to do something has the most sensible name, and a new developer will be most inclined to turn to that thing with the sensible name, the thing with the complicated name. I actually did not know that your epigraph stuff was in somewhere else rather than grafting. I think I might have gone to grafting if I did.
Yeah. And it's called motif grafting instead of grafting, so yeah. Okay, and well, so the idea here is like, you see, if you go to protocols 4, then things start to complicate into the next level, right? So in protocols 4, you already find things to work with membranes and everything, right? So my invitation for you is like, oh well, also Andrew put something there like allows you to tweak the weights and then redesign your structure. So the idea of this is like, if you are, I don't know, doing like a prediction of something, let's say a loop or whatever, then you can use these optimized weights in order to try to reproduce better what you will find in natives, and then use these optimized weights to run your structure. So again, it's reparameterizing the Rosetta in order to better fit you, right? So
reference energies are a linear correction term to a non-linear landscape.
there are many ways
There are bad solutions to the problem.
but so that means there are many combinations that give you the answer that you are looking for. It doesn't mean that is correct, right? So
there's no solution that will give you a good answer. That's the main problem. So don't rely on reference weights.
So that was the brief history I wanted to tell you about protocols 3, protocols 4. If you know anything I didn't say and you want to share, please. This is the best moment. And I wanted to cover extensively this, so I give you here a couple of comments that let you know what are all the things that are in protocols 3 and protocols 4. And these comments are so powerful that if you change the numbers there, it even tells you what is in protocols 5 and protocols 6, right? So please go ahead and take a look to all the things that are there. You will find that sometimes they are super counterintuitive, and one of these days you're going to be writing a protocol and you will be trying to figure out why is it that we don't have something that makes this? Why we have a million lines of code and we don't have something that allows you to do this simple operation? And that day, please don't put it in protocol 6, put it in core or below, okay? Thank you very much.